Hey everybody, this is Larry. This is day 23rd of the Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. Today's problem is 1048, longest string chain. So word A is a predecessor of word B if we can insert one letter to make it B. Okay. So it doesn't go, okay. Okay. So the longest length can be 10, 16. I mean, there are a couple of ways you can think about this. I think it's just about I mean, I think it's just about how to kind of phrase it to pre-process it. I think the naive pre-processing is probably good enough. And then just do like a breadth first search type thing. I mean, and you could think of it maybe as a dynamic programming. I mean, the breadth first search isn't really like a breadth first search in the same sense that it is um, a shortest path, but it is going to be like a dynamic programming, right? Because in dynamic programming, as I always kind of go through it, there are two ways. There's a bottom up and then there's a top down. And when I think about breadth first search in that scheme, it is more of a bottoms up, but just in a way that you just make sure that you have that ordering. And I guess it doesn't have to be a breadth first search, but I think because you could just do a regular search or regular sort, and then we can kind of get started. Let's get started. I think that's generally the idea, though. Dynamic programming. Let's kind of sort, but if we want to actually sort by, actually the length of the word, right? Because we want the smallest characters to be first, and that's all we need. And there are two ways to kind of think about it. One is looking forward, or the other way is looking back. I'll just do the looking back one, right? Because it's easier to kind of, maybe it is. It's easier to delete characters versus adding a character. Because if you want to add character, you have to kind of essentially brute force all 26 times n. Times L, where L is the length of a character or length of a word, because that's just like inserting in those things. Where if you delete a character, it's easy, right? You only have L characters to delete, so it's a factor of 26 or alpha for the size of the alphabet faster. So okay, let's do that then. Right. So then best of word is maybe like longest is equal to 1 being itself. So then here we do right, and then we'll go for word. So basically for each character we want to remove it, so let's just say, and there probably is a more cleaner way to write this, but I'm just going to write it the lazy sloppy way, given that n is 1000 and L is equal to 16. We can optimize these for sure, but it's fine. Right. Like you can also just with L is equal to 16, you could actually even use some sort of hashing, right? Or like some sort of hashing to kind of like jiggle the things in a slightly cleaner way, but I think it's fine. So so it goes up to I plus word of I plus 1 maybe, I think. Let's print it out real quick. I'm kind of always a little bit bad about this, right? So okay, so make sure that I get every character. So BA goes from A, B, BCA goes to BCA, BA, and then BC. Okay, that's good. That's it. It's very easy to do off by 1 in this, or at least for me. I think more people have more practice, right? So if current is in best, then longest is equal to max longest best of current plus 1, right? That's just like extending it by 1. This is bottoms up, and and then that just something like this would be fine, right? And you don't even need to do another loop. Maybe we can just do like longest or best. That's a terrible name, but okay, fine. All right. that should be good. Let's give it a spin. Let's give it another spin. Hopefully I didn't miss an edge case. And yeah, why was it so slow last time? I guess we'll take a look. But what's the complexity here? This is n log n. N log n times L. L is this. I guess no. I guess length is O of 1 for most reasonable smart things. So yeah, so just n log n. Because yeah, it only sorts on the key, so you don't even need to know the L about it. And then here, this is for each word, so that's O of n. And then this is O of L. And this is another O of L, so it becomes L squared. But this lookup is O of 1, so this is just in total O of n times L times L. You can probably do something smart with like some shifting and adding things, probably, or even just do it like, I don't know, to take advantage of prefix or something like this. Yeah, I think you could take the L out of it, so that you can make it like O times L plus L or something like this, which is obviously unable. But I'm not worried about it that much. Yeah, this is dynamic programming. That's all I have for this one. What did I do last time? That was so slow. Oh, I did the n square longest path in the DAG. I guess that's fine. I mean, I did notice this, that n is only 1,000, so definitely if you did it that way, it would have been fine. And that's, if you watch that video, that's probably what I said. This is much faster for L square is less than n. So, and yeah. So it seems like every other time I did it, well, this time I did it that way. Every other time I did it the fast way and a slow way. I don't know if there's any good pattern about it. But I mean, you know, at the end of the day, both kind of works. And technically, you know, if you look at this and you be like, oh, but this is slower. Well, it really depends on your L's and N's, right? So it depends on your input. And technically this is, I kind of missed a step. I said this a little bit, but this is actually n times L times L times n log n, right? For obvious reasons of this sorting. But yeah, at the end of the day, you know, it just depends on the L's and the N's. If n is always going to be less than, I don't know, 200 or something like this, so because L could be 16, then like maybe it's faster to, you know, this way, right? Or the other way, or whatever, right? Or the other way would be much faster if L is consistently big or something like this. But, you know, like, we don't know what the input's going to be, as long as reasonable, it's just fine. In theory, I guess in practice, not in theory, but in theory, or in practice, in theory, what you can do and what people might do is to just kind of have if statements, right? Like, you know, one is you would benchmark it so that you actually know kind of roughly where, you know, when to flip over. And then with those kind of benchmarked constants, you'll be like, okay, if this condition holds, use this one. If the other condition holds, then use the other one, and then just pick whichever one's faster. There are a lot of constants in these things, even beyond just the time complexity. So definitely, you know, it's something that you would most likely find experimentally. But yeah, cool. That's all I have for this one. Let me know what you think. Yeah, stay good, stay healthy, to good mental health. I'm gonna take a good nap. See you later and take care. Bye bye.